Hello and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the International Conference on Software Engineering, as well as select keynote speakers and distinguished paper authors. I am Will Trace, Lockheed Martin Fellow Emeritus and former chair of ACM SIGSOFT, the Special Interest Group on Software Engineering. It is my pleasure to welcome you today. Before we get started, for those people joining us for the first time, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you are experiencing problems, which I guarantee some of you might, with the slides or audio, press the F5 key in Windows, Command R on the Mac, or simply refresh your browser on a mobile device, or you can just close and relaunch the presentation. The control volume, adjust the master volume on your computer. If you have any questions during the webinar, please type them into the Q&A box at any time during the webinar and click the submit button. At the end of the presentation, you will have time to respond to these questions. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is Software Product Line Analysis and Construction by David Weiss. David is an emeritus professor of software engineering at Iowa State University and co-founder of Sustainable Software LLC. Previously, he worked at Bell Labs and Avaya Labs. His best-known works are the goal question metric approach to software measurement, his work on modular structure of software systems, and his work in software product line engineering as the co-inventor of the FAST process. David is a fellow of IEEE. David, without further ado, take it away.
Thank you very much, Will, and welcome to all of you. Thank you for joining us today. I'd like to just say one or two really quick things. If you heard my last webinar on architecture, you will recognize a lot of what I have to say as being built on the idea of software architectures for families. The topic I'm going to talk about today is really software product line engineering. If you look at the first slide there down in the left-hand corner, you will see the cover of a book called Software Product Line Engineering, a family-based software development process. That is the first book on software product line engineering, and I am happy and proud to say that I am a co-author of that book. And a lot of what I'm going to say today comes out of that book, so if you are really interested in this subject and want to see it in more detail, because we will not have time for a lot of detail today, you can go and get that book and take a look at it. There are also a number of papers on the subject, or you can just send me email or ask questions at the end of the webinar. That's the only advertisement I will give for the book. I will also say that having given these webinars before, I know that sometimes the rate at which I change slides is different than the rate at which you see the slides. So you may find that sometimes I will hesitate a little bit before changing slides just to make sure we're all consistent and we're all seeing the same thing. So here's what I'm going to talk about today. First, I'm going to talk about families and define a family and what a family is. Then we'll talk about the economics, because this is where the advantages of product lines come from. You get an distinct economic advantage from using product lines. I will then define a product line, and then I'm going to talk about how you create a product line, and what I will do is do that by example. So I will use a particular example. Also, one more point. All of the process that I'm going to talk about for creating product lines comes out of an approach called the FAST process for product line engineering. There are other processes as well. So what I am not going to do today is a discussion of all the different processes for product line engineering and a comparison of them. I'm just going to focus on one, so you get a very clear idea of what product line engineering is and can do, and how, in fact, you might use it if you want to use it for your own purposes or your own company. As I say, I'll define the family. I'll give a few examples. I'll talk about the economics of families. I'll define a product line, tell you the basic assumptions underlying them, and then I'll talk about how to create a product line, and I'll use a real example in doing that. I will warn you right now at the moment, it is a real example in the sense that this product line exists. However, I and others have created more or less hypothetical design for it. So the design that you see that we use for the product line is not necessarily the one that's being used in practice. We just do this in order to have a good way to demonstrate things. Well, let's start with something a little more fundamental, shall we say. This is a definition of software engineering. So software engineering is the multi-person development of multi-version programs. This was a definition that was proposed by Brian Randall in the late 1960s, I think around 1968 or 1969. And when I asked Brian when he did it and all, he said, oh, it wasn't me, it was David Parnas who actually defined it. And then when I went and asked David Parnas, he said, oh, no, it wasn't me, it was Brian Randall who actually did it. So not exactly clear which one first enunciated this. But if you think about this, if you're a successful software developer and you have a number of different customers, what ends up happening is that you start developing a version of your software for each customer. And each customer is going to have somewhat different requirements and desires and wishes, and you may well end up creating a whole set of versions for each particular customer. This is why we think of software engineering as being multi-version. If you're successful, you're going to create lots of different versions of your product. In order to do that, you need to have a team of people. So it's really the multi-person development. And when I say a team of people, I'm not thinking just of people who are doing architecture and coding and testing, thinking of people who are doing marketing. I'm thinking of project management, thinking of the customers, of the people who provide the services to the customers, the developers, the architects, the testers, and of course, the users. These are all people who are involved in the development of your software. If you've been in software development for any period of time, any length of time, I'm sure you will recognize this, especially if you think of yourself as a successful developer. So let's talk about families, or let me talk about families for a moment, and I'll give you the definition of family. Family, we consider a set of programs to constitute a family whenever it is worthwhile to study programs from the set by first studying the common properties of the set and then determining the special properties of the individual family members. We're going to call the common properties commonalities. We're going to call the special properties of the individual family members variabilities. This was a definition from David Parnas, also quite a while ago, who showed how to use, the idea of families in software development. Notice that I have underlined worthwhile. Whenever it is worthwhile to study programs from the set. So you only think about families when it's worthwhile to create a family. And that means there's some economic justification, and I will talk a little bit about exactly how you go about looking at the economics for this. So what are some examples? So software engineering was not the first place to look at families and decide to try to use families to do product line engineering. Here are a few other examples. Airbus airplanes form a family. What's common among them? They all have the same cockpit. Why did they do that? Because it makes it easier to maintain the different airplanes, and also so that the pilots don't have to learn a new cockpit for every airplane. This turned out to give them a big advantage over Boeing. When they first started coming out with the Airbuses, they said, here, we have this family of planes. It's cheaper for you. Maintenance is going to cost less. You don't have to keep retraining your pilots. And Boeing, which worried a little bit about the competition, then said, oh, we have a family too. Look, we have the 707, the 727, the 737. Unfortunately, it was a family in name only and did not at that time have the same qualities as the Airbus families. And if we look at the computer field, I don't know how many of you have seen an IBM 360 or remember IBM 360s. IBM 360 was the first really big successful computer for IBM to help them take over the market. The IBM 360 was deliberately defined as a family. If you were a user, you could buy an IBM 360 that was relatively slow and didn't have much memory. And then IBM's idea was when you came to them and said, hey, I need more memory for my computer and it's too slow, they would say, oh, you just need to step up to the next model. And by the way, when you do that, all of the programs you currently have will still run. So it's really easy. So they captured a very large market by doing that. Anytime you wanted to improve your computing capabilities, you just step up to another model of the 360. All the software you had would still run. So you can imagine what was common to them was they all had the same underlying instruction set architecture. So the same instructions would run on any different computer. They also all had the same interface. I don't know if any of you ever remember the 360 operating system. I do. And probably I shouldn't say this in public. That was a terrible interface. And you had to use it no matter what 360 you were using. Internet browsers, think about it. What do internet browsers have in common? They all render HTML. Linux, smartphones, companies like Apple have become really successful because they have developed a family of smartphones. You can buy a smartphone with different characteristics, but they all operate the same way. They all have the same user interface. The example I'm going to use today are called floating weather stations. If you want to get a peek ahead, you can click on that link there. I'm not going to do that since we don't really have too much time. But it turns out that all over the world, there are these buoys that monitor the weather and the atmosphere, and atmospheric conditions. They float around at sea. Some of them are anchored in different places, and they allow you to get a good view of what the weather is like in different parts of the world, and they transmit all this over the web. There's a history that's maintained. You can look at climate, and you can look at climate change. So as you can imagine, the floating weather stations have become more and more important lately to try to understand what's happening with our climate and how our climate is changing. Okay, so those are a few examples, and as I say, we'll come back to the floating weather station in more detail a little bit later. And remember what I said earlier, floating weather stations actually exist. They're out there. They collect data. They send the data over the web. But the design that we're going to use is a family-oriented design. I do not really know if the floating weather stations use that particular design. They probably do not. But we will use it as an example because it helps to understand exactly what families are and how they can be applied. First, let's take a look at the economics. So this graph is a somewhat simplified version of what the cost is as you increase the number of family members. And it assumes that the cost for each family member is roughly the same. So you essentially got a straight line there. So the cumulative cost increases over time. Well, what we would like to do with product line engineering is change the slope of that line, put in a little initial investment, and then change the slope so that the cost of producing each family member is a lot less than if you use the current practice where you go in there and you sort of twiddle the code for the family member each time. So an interesting question here is if I do that, exactly when do I get a payoff? How many family members do I have to produce in order to suddenly start making a profit out of the product line engineering approach, a better profit than I've been making with my current practice? I'll let you think about that for a moment. See if you can guess how many family members you might need. But I will tell you that in order to determine this, I started doing a study of the families that where we were using product line engineering, and I came out with a particular number. for where we suddenly started having an advantage in product line engineering. And I looked at that and I thought, gee, I wonder if anybody else has ever done this. And just about that time, a paper came out, and it was a paper from Barry Boehm. I don't know if many of you know who Barry Boehm is, but Barry is a professor at USC, I believe. And he was a researcher for a long time, well respected, and his paper had the same result as what I had discovered myself. So I thought, well, if somebody like that has come up with the same numbers as me, maybe there's some justification for this number. And there it is on this current slide. It's between 2 and 3 family members. So once you've started using product line engineering, you see a beneficial result after about, well, let's say three family members. That's not too bad. That's relatively few. If you want to see it a little more precisely, this is a graph that shows the cumulative savings as a function of the number of family members, the cost per family member as expressed by the cost difference between, shall we say, the classical way of doing things and the product line engineering way of doing things, that's CT minus CF there, minus the initial investment. So when n gets to be about 3, you get the payback point. So your savings suddenly become positive. So this is something that's a little more realistic when it comes to the economics of families. What happens here is that when you start out, the first member usually costs you more than the next one because you're learning. You're learning about the family and how to produce it. And then your next version is cheaper to produce. And then slowly over time, the cost rises. Well, the cost rises for lots of different reasons. I won't go into a lot of them, but as it turns out, as you make more changes, things get more complex, there are more errors. And then after a certain point, you're spending all your time correcting errors and trying to make changes. There's a line there called the Klein horizon that shows where sort of you no longer have a viable a family member or number of families. It's called the Klein horizon because it was pointed out to me by a colleague of mine named John Klein, who was an architect. And he said, you know, after this point, it's really not worth it. You better go back and just redo the whole thing. So what we're trying to do with product line engineering is smooth things out. So you don't really have that Klein horizon, and you can go on producing family members as long as you want or over some long period of time. I can tell you there are places that have used this idea and have families that have been around for, say, 20 or 30 years. Okay, so let's try to make the idea of a product line a little more precise. We've got the idea of a family now, and remember, when you have a family, you understand what the family members have in common, and you've decided that it's worthwhile to make a family because of those commonalities, and you understand how they vary, so that there are variabilities. So a product line, then, is a family of products designed to take advantage of the family's common aspects and predicted variabilities. Notice I said predicted variabilities. That means you have to predict what the variabilities are going to be and, in fact, what the possible values of the variabilities are going to be. And a little bit later, I'll go into that, and we'll see how you might do that, and we'll use the floating weather station product line as an example. It may turn out that a product line could be decomposed into subfamilies, where each subfamily contributes a member to members of the product line, and the subfamilies may themselves be product lines. I'll give you an example. It's not from software, but that's everybody usually understands pretty easily. Automobiles are usually produced as families, right? When you buy an automobile, you can go in and you can get, say, a different engine, maybe. You can get automatic versus manual, gear shift, transmission, and there are certain variabilities there. In fact, last time I went to buy a car, I went in and they said, here's a list of things that you can choose. You know, you could choose to have door locks such that when you lock the driver door, all the other doors lock. Or when you unlock the driver door, all the other doors unlock. There were a whole bunch of things they gave me that were options, so that when they built a car and delivered the car to me, those options were in place. So cars are usually produced as product lines, as families. However, if you look at cars, look at tires on the cars, you discover you can get different tires, right? You can buy lots of different tires for your car. So the tires form a product line as well. So they are sort of a subfamily of the family of automobiles. If you want to see some examples of product lines, there's something called the Product Line Hall of Fame. There's a link there to go look at it, but here are a few examples. Philips has software for its televisions. These were designed as a product line. Bosch has produced engine control software for automobiles, and their engine control software is designed and implemented as a product line. Lucent Technologies had switch maintenance software. I will confess that they did that as a product line while I worked at Lucent in Bell Labs, and we worked on the switch maintenance software together. And this is software that helps keep the switch operating and maintain the switch in the event that some of the equipment connected to the switch and used by the switch fails, so they can switch in backups. So that we designed as a product line. There's a company in China called Physcan that produces baggage inspection systems. So when you go through an airport in China and your bags go through the inspection system, it's a Physcan inspection system. That inspection system was designed as a product line as well, and it doesn't just do baggage that people carry on. It does cargo that's loaded onto planes as well, and various other things. If you go to the Hall of Fame website, you will see descriptions of each of these product lines, why they're a product line, and why they considered it worthwhile to create a product line from them. Okay, one more thing about product lines, the idea of product lines, and then we're going to go on to the process and an example. There are three key underlying assumptions for product lines. I have phrased these assumptions as hypotheses. First, I call the redevelopment hypothesis. That says most software development is mostly redevelopment. Those of you who are experienced may recognize this. You're redoing software over and over again for a variety of reasons. You may move to a different platform. You may decide to use a different language, a different operating system. It may be that some of the hardware that you control has changed and you've got to redevelop the controllers for it. Any one of a number of reasons, but most of the time you're doing redevelopment. Bugs also are in that category. You can think of them as redevelopment. So the redevelopment hypothesis says that most software development is mostly redevelopment. Second hypothesis I call the Oracle hypothesis. The Oracle hypothesis says it is possible to predict the changes that are likely to be needed to a system over its lifetime. That says, if you know the system and are familiar with it, you can predict the changes that are likely to occur. Now, a lot of people are very skeptical about this. However, when I say changes that are likely to be needed, I really mean types of changes, classes of changes. So I'm not sure you can predict every individual change, but let me give you an example. Think about disk drives. Over the years, what's happened with disk drives is that they've gotten bigger and faster, and the approach, the protocol that they use for transmitting data back and forth to your computer has become standardized over the years. So you could have predicted, say, 5 or 10 years ago that hard drives would get bigger and bigger. The other day I saw I think it was a 4 terabyte hard drive advertised for $100 or so, which amazes me because I recall first hard drive I ever bought was 20 megabytes, and it cost me about $1,200, and I thought I would never need another hard drive in my life. Now, it's quite common for people to have several terabytes worth of hard drive data on their personal computers. And on the computer you use at work, maybe they have 20 terabytes. Maybe they have 100 terabytes, right? So the size of the disk drives has been increasing, and that would have been an easy prediction to make a few years ago, and you can predict that it's still going to increase. Same thing with the speed of the hard drives. Same thing with the protocols that they use. So these are all types of changes. I can't say that I know that the hard drive is going to go from 1 terabyte to 1.25 terabytes in the next year. That's maybe a little too hard to do. You might be able to do that if you're in the hard drive business, but you can definitely predict certain types of changes. And by the way, I'll talk more about this in a little while, but when you start thinking about the changes and saying, well, how can I predict that? How can I know what kinds of changes might occur? One way is to look back at the changes that have occurred in the past. Oh, hard drives, the size of hard drives has been increasing. You know, it's been increasing for 20 years now. Oh, maybe it's going to keep increasing. So one way to do that is to look back at changes. And I will add to that today, that's a lot easier to do than it used to be. Why? Because we have things where we now record all the changes that have been made to our software over time. We have repositories like Git and GitHub or SVN, a variety of other repositories that more and more people and more companies are using, and they allow you to go back and track all the changes that you've made in the past. So you can go and look and try to analyze it and use that to help predict. You can also look at technology and see how technology is changing. Could you have predicted SSD drives? I don't know. If you were in the hard drive business, particularly in the research business, the hard drives, you might have been able to do that. So you can look at technology and what are the latest research issues or what are the researchers looking at. Well, maybe that's going to result in certain kinds of changes you're going to have to accommodate in the future. Okay, so we have the redevelopment hypothesis that says most software development is mostly redevelopment. We have the Oracle hypothesis that says it's possible to predict the changes that are likely to be needed to a system over its lifetime. And then there is one more key hypothesis that I call the organizational hypothesis. The organizational hypothesis says it's possible to organize both your software and your organization that develops and maintains the software in such a way as to take advantage of predicted changes. You may think that's obvious. I don't. Or you may not think that's obvious, but you need to be able to organize so that you can take advantage of the predicted changes. There was a time in my career when I was working on the architecture for a project, and the head of the project came to me and he said, great, we really want to use this new idea of product lines and your architecture for it. He said, tell me now how I should organize my people for this. And I said to him, well, I can't really tell you until I'm finished with the architecture, because the architecture determines the different tasks you're going to need to do, and then we can start assigning people to it so we know as to who does what. So you have to understand that architecture and lots of other issues affect your organization. These days, it's even more difficult because organizations are likely to be distributed around the world, and you have to think about how you're going to assign different tasks to different parts of your organization, and your architecture will definitely be key in doing that. Okay, so we have three hypotheses. Oh, so let me just say, the reason I think it is possible to organize both your software and the organization that develops and maintains it is because I've seen it done. And I will talk to you a little bit about how you might do that. But again, if you had attended my talk on my webinar on software architecture, you will see that I covered that topic, even though I might not have called it organizational, but I covered that topic. And the key is when you create the software, you have to think of yourself as creating modules that are work assignments for people. Okay. So what would a product line engineering process look like? Now, this is different than the agile processes that are very popular today, or even older processes, what we have are two key sub-processes. One is called domain engineering, and one is called product engineering. What happens in domain engineering is you define your family. And as part of that, you're going to have to define the commonalities and variabilities for the family. Then what you're going to do is create an environment that allows you to generate family members. Yes, I said generate. The goal here is to be able to generate members of the family so that when you have a user who says, hey, I want this, 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 and that, you say, okay, no problem. I'll just put that into my generator and I'll generate it. Now, you may think I'm being a little lighthearted or something like that, but in fact, in most cases, this turns out to be quite doable and quite worthwhile. Often, you do not do it on the first iteration, but by the time you've gotten through, say, 3 or 4 or 5 family members, you understand how to create the generator. So you need a product engineering environment that's going to allow your product engineers to generate family members. So that's essentially what's happening in product engineering. You have a set of product engineers, and those product engineers will talk with the customers, see what products they want, and use the product engineering environment to produce those products. And as I say, what you want to get to after a while is to be able to generate those products. Now, this is a feedback loop here from product engineering to domain engineering, because after all, the product engineers have to go back to the domain engineers and say, hey, look, this environment isn't working too well for me, or I have customers who are asking for things that you never included in the environment. So you need to have some kind of feedback loop there so that the domain engineers can improve the product engineering environment over time. Just like any software development effort, you improve things as you go, at least in a lot of them. I know there are places where they don't do that. So we think of the domain engineering as an investment in the family. And we can think of the family as a domain. Domain is another name, really, for family. The product engineering is where we get payback. So the product engineering produces products. I'm not really going to spend a lot of time on these individual aspects. I will go through an example so you can see. But let me just say that this is really quite different from agile development. You might, once you've done the domain engineering and have the product engineering environment, that you will, in fact, be able to do something like agile, where for each product you can very quickly produce a product. But you do it somewhat differently than people do with agile. And generally in agile, my impression these days is that people don't pay as much attention to architecture as they should, so you have a lot of trouble trying to produce a product line. Okay, won't say more about that. So let's look at the example. So the example I'm going to use is the floating weather station family. And the floating weather stations are buoys. They're deployed at sea, and I've simplified this so that we can think of them as periodically reporting the current wind speed via messages sent by radio. In fact, the actual buoys report a lot more than wind speed. They can do water temperature, air temperature, and a number of other things. Every member of the family has an onboard computer that controls the operation of the buoy while it's at sea, make sure that the data are collected from different sensors, and that the data are sent back. If you go to that website, you will see this little map. It shows where all the buoys in the world are. And that picture there is a picture of a buoy floating at sea. And if you want to, you can click on an individual buoy in that map and bring up the data from that buoy. And it's what I've done here. And this is, you can see again a picture of the buoy. I wouldn't worry too much about exactly what data it's showing. I think that's might be wave height in that little graph. Here's some other data that you might see, but just assume that what you can do is see data from individual buoy and some history of that data. If you're really interested in this and you're at the website, click on one of the buoys and take a look. Some of the buoys actually float around. some of the buoys are just fixed. Here, so we can think of the buoys as forming a family. Why? Because all of the buoys report on environmental data. They all have one onboard computer. They all have a variety of sensors that allow them to monitor monitor the environmental data. So here are a few ways to distinguish members of the family, and there at the bottom are pictures of different family members. So if I have a buoy that's measuring some environmental aspect, the resolution on the buoy might vary. It might be low, might be high. In fact, in practice, there's probably a lot of different resolutions, but we'll just use low versus high for the moment. I might have different sensor types. I might have air temperature, water temperature, wave height, wind speed, barometric pressure. I might have just one type on a buoy. I might have several different types on a buoy. Why is that? Well, one obvious reason is I'm interested in different parameters in different places. Another obvious reason is that the more sensors I have, the more it costs. The amount of time for which data is retained may vary. Some buoys might retain their data for, say, a month. Some might only do it for a week. Some might only do it for a couple of days. You can see the amount of memory that you're going to need on board is going to vary because of that. So we're just going to think of data retention as being short, medium, and long. And then there are transmission capabilities. So the buoy is sending its information, its data out, essentially by radio. It's transmitting it. It may be transmitting it to land stations. It might be transmitting it to a nearby ship. So a ship passing by might ask a buoy what the conditions have been recently. It might be transmitting to satellites so that it can be retransmitted all over the world, say. So here are a few things that might vary. We were going to call these variabilities. So these are 4 variabilities in the floating weather station family. I'd like to know whether it's really worthwhile to think of the floating weather stations as buoys. So I'm going to try to do a little economic model to qualify this as a family. Let's say the target market for floating weather stations, and this is all hypothetical, is 1,000 new floating weather stations needed in the next few years to try to measure global warming and its effects. Let's say a floating weather station will cost $9,000 to produce, and we'll sell them for $10,000 each. Let's say our initial investment will be $50,000. And these are all hypothetical numbers, but you should get the idea that I need to have some idea of what these numbers are. So I know what the profit per floating weather station is. It's going to be $1,000. My total profit is going to be the number of floating weather stations I sell times that profit per floating weather station, which is 1,000, minus my initial investment, which will be $50,000. So this is a really simple economic model, but it allows you to have a good idea of whether or not it's going to be worthwhile to think of the floating weather stations as a family. And you can go back and think about this and apply this to whatever family you're working on, to whatever software you're working on. You can say, do I really have a family? Is there really enough in common here? Oh, well, let me see. How much am I going to sell these for? How many of these am I going to sell? And so forth. So you can create your own model like this. Let me also make the point here that this is a relatively quick and easy thing to do, and it gives you a lot of insight into your product. Let me expound on this example just a little bit for that point. Suppose I say, I've heard that the Whale Watchers Society would like to know where the whales are and what the population of whales is. Maybe I could find a sensor that will monitor whales passing by my buoy and see, and then be able to sell buoys to the whale watchers. Oh, well, how much would a whale watching sensor cost? How much would it cost me to modify my software to put that in there? How much could I sell it for? All right, so I'm sure you get the idea. Lots of different possibilities there. So if I quantify this a little better, this is for that example I gave. Here's a profit as a function of the number of members sold, and it looks like you get paid back around 5 members here. It's rather conservative. All right, so now how do I go about defining my family? I've tossed around words like commonality and variability. So what's a commonality? Commonality is an assumption that is true for all members of the family. For example, one commonality is that at fixed intervals, a floating weather station monitors the wind speed at its location. That means that, say, every 30 seconds or every minute or so, the floating weather station will monitor the wind speed, will get the wind speed. Then I need to identify variabilities. Variabilities are assumptions that vary among the family members. For example, the number of wind speed sensors on a floating weather station might vary. So the number of wind speed sensor is going to be a variability. So I have commonalities. Again, these are assumptions that are true for all members of the family. I have variabilities. These are assumptions that are going to vary among family members. But I have to be a little more precise than that. So what I try to do then is identify what we call parameters of variation. This is a quantification of the range of values of variability. For example, I might say, okay, I'm going to have between 1 and 5 wind speed sensors on a buoy. That's my parameter of variation for it. So I'm going to restrict the number. This is a really key point. If you can't restrict your variabilities, you're not going to be able to design for the family because you're not going to be able to design for some known restricted number of parameter values. Once we understand what the commonalities and variabilities for the family are, we do something called the commonality variability analysis, and we document it. I'll just say one really quick point about documenting. That enables people in the future to understand what you did and why you did it. All right, here are a few commonalities and variabilities for the floating weather station. The commonalities are labeled C, so C1 says at fixed intervals, the floating weather station monitors the wind speed at its location. The variabilities are labeled with V's, so V1 is the number of wind speed sensors on a floating weather station may vary. The reason some things are in red is that there are specific technical terms that need to be defined somewhere in a dictionary, and I'm not going to go into that. Here are a few parameters of variation. So, for example, first parameter of variation, P1, is the sensor count. The V1 there says that is related to variability 1. This is the number of wind sensors. The value says from 1 to 5. And one more really key thing is the binding time. The binding time is a time at which I need to decide what the value of the parameter should be. And this says the binding time is going to be its specification time, which means when I specify a particular floating weather station buoy. And then there's a default. So the default is 1 sensor. But I can always change it anywhere from 1 to 5. Second parameter of variation is the sensor period. This is the amount of time between readings of the sensor. And that could be anywhere from 1 to 600 seconds. Again, find the specification time, and the default is 5. So you can see I need to go through all my variabilities and identify the range of variation for each one. Again, this gives me better insight into my system and what I'm producing, even if I don't do anything else. Identify commonalities and variabilities helps me. Once I have the parameters of variation, I can create a decision model. So the decision model lists the decisions that you must make to specify a product in the family, in the product line. For example, how many wind speed sensors will the floating weather station have? It's a decision that somebody has to make. The second part of the decision model is in what order must I make decisions? So, for example, I have to decide on the maximum number of wind speed sensors before deciding the number of wind speed sensors I'm going to have of each resolution. So some wind speed sensors may have low resolution, some may have 5, but there's a certain maximum number of sensors that I'm going to have, and the sum of the low resolution plus high resolution can't exceed the maximum. Then I have constraints among decisions. And in fact, what I just gave you is a constraint. If the total number of wind speed sensors is N, number of high resolution sensors is K, the number of low resolution sensors must be N minus K. Oh, the most sensors I can have is 5, and I'm going to have 3 low resolution, then I can only have 2 high resolution. So there are constraints among the decisions. So here's a little example of the decision model. Going from left to right, first I have the parameter variation. I have the meaning of the parameter variation. I have the value set. So if for the parameter maximum sensor period, the value set is 1 to 600. I have a default value, which is 600. There are no constraints on this one. The binding time is when I create the translator that's going to produce, that's going to generate the floating weather station software for me. And then on the far right is something I haven't talked about. These are the modules in the architecture that I need in order to implement this particular parameter variation. And if you look down through that list, I have a sensor monitor, probably not very surprising. I have an averager. I have a data banker, which is just really a little database. I have a message generation module and a number of different modules. Key point to understand is that I'm able to do my architecture and know what the modules in the architecture should be by going back and looking at the variabilities, because I know I want each variability to be independently changeable unless there's some constraint, and that means I want each variability to be, how to change the variability to be the secret of a particular module. It's a decision hidden in the module. So knowing what the variabilities are gives me a big step up in creating my architecture. And the next slide is just more of the decision model. Notice I have things like the weight of the high resolution sensors in calculating the average, how long the history is going to be, what types of message I'm going to be able to send, how many sensors I'm going to have, what the sensor periods are, et cetera. And again, for each one of these, have the meaning, a value set, constraints, and notice in the sensor count there's constraints. That's exactly the constraint I talked about before. There's a binding time for each decision, so I have to know when that decision has to be made, and there's a set of modules that I need. Notice that if my architecture contains a users relation that shows for each module which other modules it uses, then in the module section, those modules determine what modules are going to be included. Those modules and the modules that they use determine what modules are going to be included in each floating weather station family member. Now, for floating weather stations, it doesn't make too much difference. Usually you get pretty much all the modules on each floating weather station. But you can imagine if there's more variability, then some of your family members will have a different set of modules than other family members. That can make for, if you haven't been using product line engineering, that can make for some difficulties in maintenance. One other really quick point, you can think of variabilities as an option. That is, that each variability gives you an option in features, shall we say, for the product line, and those features, if you implement them, will bring you a certain profit, so a certain return. So if you think of variabilities as an option, then you can say, well, how much is this option worth? How much is this variability worth? I won't go into that too much more. I'll just say it's a good research project to figure out how to calculate the options. Identifying variabilities. Well, this is something I talked about before. You looked at what's changed in the past. So you look at your history of past changes. You look at the technology that's developing. So you say, what research is in progress? And then, of course, you go to your customers. You look at what your customers are using and then what they're asking for. So it may be they want more accurate, more detailed results for climate change. So you might need to put in different sensors, more accurate sensors. Or maybe you want to put in a whale sensor for some new customers. Okay, once you have done that, once you have created the decision model, the architecture, written the code to implement the architecture, you can produce a little generator that will generate the code for a particular family member. Now, I'm not going to show you the details of that. That's a whole other talk in itself. But essentially what you do is you give your users a little tool, web tool, if you like, where they can specify exactly what the value is for each decision. So, for example, here, this is allowing you to specify the number of wind speed sensors, the weight of the high resolution sensors, and the sensor period, the transmission period, etc. Once you know all these things, it's like those options on the cars I was talking about, then your generator can generate the family member. Once you have a family member generated, this is a little more advanced, but in a lot of cases, once they have a family well-defined, they're able to generate family members, you can create a simulator. So this simulator, once you have made the decisions, will show you what it's like when the floating weather station is running. So it shows you the values that you get from the different sensors out of it. That means you can do all your testing at your desk if you like, if you trust the simulator, and if you have a good simulator. You could sit there and see whether or not there are any bugs in the system, whether it's producing the right things. People who have done this gain a tremendous advantage, particularly in situations where you have real-time systems. Why? Because they don't have to go into a laboratory. They don't have to go out to the ocean to try to test their systems. Okay, quick summary here. Product lines take advantage of commonalities and variabilities to make software development more efficient. But it's really important to constrain the variabilities, and the efficiency you get generally is a factor of 3 to 5. That is, your productivity improves by a factor of about 3 to 5. Reorganizing the way you do software production to take advantage of the family viewpoint is really the key to improvement. What we're trying to do is generate code and documentation really from a model. That little website I showed you a minute ago where you enter the decisions, the decision model is the thing you want to use to do generation. That's the goal. Well, let me just end here with a little quote from Isaac Newton. Newton said, "If I've seen farther than others, it is because I've stood on the shoulders of giants." People have been working on these ideas for a long time, and we now can have a little fruition from them and greatly improve our software development processes as a result. Okay, I am now open to questions. I just want to point out that there is a survey at the end. We would appreciate you filling out that survey and sending it in. Okay, questions, Will?
Yes, thanks, David. And I once again encourage all the attendees to use the Q&A box to submit a question for David, and we'll get around to it. Now, first question. Low code is a commercial marketing name which seems to apply to product line architectures. Are you familiar with it? And would you make any comments on whether this is just rebranding of the concept of product line architecture?
So I'm not familiar with that particular one, but I know a number of different companies that, in fact, will help you and teach you how to do software product line engineering and give you the tools to do it. So, for example, you might have noticed I'm part of a consulting group called Sustainable Software, and one of the things we offer is to help people do product line engineering. There's a company I know, maybe I shouldn't single out anyone, but I'm going to, called Big Lever that's been doing this for years. If you go to the software product line conference, to the proceedings from it, you will see several different companies that produce the tools and help other companies do product line engineering. The one you mentioned, I'm not particularly familiar with. Sorry.
Okay. Well, once again, it's just a marketing term that seems to be showing up in the IT industry, relevant to product line approach. Second question. Pardon me?
Go ahead.
Okay. Are there any open source product line efforts?
Yes. I will say that there are. I think Linux is one. Now, I don't think that Linux uses a formal product line approach, but it's definitely a family. It definitely has a specific architecture that I think you might think of as a product line architecture. And the reason for that, of course, is Linus Torvalds, who created it that way in the first place. And there are others that I've seen as well.
Okay. Are there tools to reverse engineer product lines? And, I would assume that means that you have evolution of software products that you would then, instead of starting from scratch, somehow or another reverse engineer it to provide you with a basis for components or analysis or variability?
Thank you for asking this question. It opens up a whole issue, a whole set of issues that I didn't talk about at all. But let me just very quickly, since we have a couple minutes left, very quickly mention that if you have an existing system and you think, gee, maybe I have a family here, I'd like to try to create a product line out of it, there is a process that you can go through step by step, basically. And essentially, what you do is you look at changes, look at where you're making the most changes, particularly the most profitable changes, and you see if you can restrict your attention to the area of the system where those changes are being made, and then create sort of a subfamily or a little family out of that area. Once you can do that so that you could generate that part of your system, then you can expand your view to other parts of the system and create a larger product line. Also, as part of this process, you may not go through the whole product line process. You might just say, okay, what are my commonalities and variabilities? Can I identify those? Yes? Okay. Now, can I modify my architecture to take advantage of the commonalities and variabilities? Well, maybe I can only do that in one place where the most profitable changes are happening and where changes are happening the most. I just change the architecture for that. So you do it bit by bit, step by step. Now, there are tools that will help you at these different steps. I'm not going to name any in particular. I'll just say companies like, say, Big Lever have such tools to help you do this. There are lots of other tools out there today. If you look around, if you look at the analysis that some people are doing based on repositories, where they say, okay, where are the changes being made? You can use tools like that, and you can use repositories like that to go back and analyze your system and say, okay, I see where we have to make the changes. I see where we have to make changes to our architecture. I see how to create a little generator. So I don't know all the tools that are available, but there are tools. And if you do a little investigation among some companies, you will find them. But the idea that you might want to take your existing system and create a product line out of it is a very common idea. And a lot of the companies that I listed in the Product Line Hall of Fame, in fact, have done that, and they've done it little by little, step by step. And one of the things you discover is each step takes a little more effort and it's a little more expensive, but gives you a little more of a return, and you get a better and better understanding of your system as you do go through this step by step. Even if you only say to yourself, what are the likely variabilities? That is going to give you a better understanding of what you need to design for, even if you don't create a product line engineering environment or a tool to do generation. Sorry for being so long on that, but it's a good question.
I'm going to try to squeeze in two more questions here. One is, you gave two examples of binding time. Do you have any more examples of what binding time types there are?
Sure. So you can think of this starting very early from the time you define requirements to the time you are writing your code. So at each step, you are making decisions. You're having to make certain decisions. So there's a binding time for each one of them. Now, when it comes to actually doing the generation, there are really two key binding times. One binding time is when you produce your generator. So if you're creating a generator to generate the members of your product line, the products in your product line, that is one key binding time, because when you make decisions there, they're often very difficult to change later on. You have to be aware of that. Second binding time, of course, is when you're writing the code, or even before when you're doing your architecture. You're making decisions about what's going to be easy to change and what's going to be hard to change, so there's a binding time there also, and that's where you really need to know your commonalities and variabilities. Then there's a binding time at which you actually do the generation, right? And that's what I call specification time in the decision model. Binding times are actually a pretty common idea. They go way back, but people often are not aware that when they're making a decision, it's going to be binding. Think of it like this. It might be binding right away. It may be that it's going to bind you for the next 30 years of your system. If you think of the spacecraft, the Voyager spacecraft, which have been out in space for 30 years, still using the same software, but they make changes to that software occasionally. They made certain decisions that they can't change 30 years ago, and those decisions are still in effect. So binding time is important to think about. One more rule?
Okay. I've got one more question that may be a quick answer because I think this is a quick answer, but there was a comment on facing the reality of agile software development that discourage writing of code and that may eventually support product lines. How do we overcome that resistance? You can just say good luck. In 30 seconds or less.
Exactly how to overcome it, but the way I would do it, I would create an architecture first and then use Agile to develop members of the family based on that architecture. But I do think you have to have an architecture, and I do think there's resistance, but the way to try to overcome the resistance is to look at the economics. Remember, early on I said you get an advantage of a factor of about 3 to 5 when you create your product line. You can't do that with Agile. It doesn't give you such an advantage.
Right. Okay, well, once again, I'm afraid we've run out of time, and thanks to David for his informative presentation and insightful answers to our questions. And thanks to you all for hanging in there and attending and participating in today's webinar. This webinar has been recorded and will be available online in a few days at http SIGSOFT resources webinar.html. You can find announcements of upcoming ACM and SIGSOFT webinars at other ACM activities at learning.acm.org and www.sigsoft.org. Note that the slides include a short survey of this webinar with a chance to suggest topics that you could hear in future webinars. So on behalf of SIGSOFT, the speaker, and myself, thanks again for joining us, and I hope you will join us again in the future. This concludes today's